Good morning, everyone. It's Dan Sandig with ICLR. Welcome to our final webinar for the year. Thanks very much for joining us. It looks like we'll have a pretty good crowd today. Today we have Sarah Stevenson and Emilio Hong from Western University, who will be talking about the Hurricane Irma damage assessment that they were involved in over the past few months. Just before we get started, I wanted to remind everybody methods for asking questions. So you can use the Q&A box that you should be able to access via the webinar screen. And please feel free to ask questions throughout the full webinar, and we'll be holding all the questions until the end, and then we'll have some time for discussion. So quick introductions to our speakers. Sarah Stevenson is a PhD student in structural engineering at Western University. Her research focuses on improving hurricane resistance of residential structures in the Caribbean. Her past work has focused on the behavior of wood frame roofs under extreme wind loads. And Sarah has participated in several post-storm assessments with Environment Canada, including surveying damages from recent tornadoes in Windsor in 2016. Emilio Hong is a research engineer at Western University, and he's currently working on a project that is looking at studying identification of tornadoes in Northern Ontario. Emilio finished his master's in engineering science in wind engineering at Western in 2017, and Emilio has also been involved in several post-damage surveys, including those associated with the Angus, Ontario tornado in 2014, the Windsor tornado of 2016, and Quebec tornadoes in 2017. So with that, I'll pass it first to Sarah.
Great, thanks, Dan. So good morning, everybody, and thank you for tuning in this morning to join us. We're going to talk to you this morning about our experience and observations from participating in damage assessments following Hurricane Irma in Florida back in September. So thanks to the support from ICLR, Emilio and I had the opportunity to travel to Florida in the week following Hurricane Irma to assist the researchers at the University of Florida in Gainesville with their preliminary damage assessments. So we kind of went all over the state and saw damage ranging from wind and tornado damage to storm surge damage and flooding. And this is a really educational experience for both of us, since our prior damage survey experience, as Dan said, has been related to tornadoes. So we saw a bit of a different survey approach. The extent of damage was obviously quite different, and the types of failure we saw were different from those that we're used to in Canada. So just to provide an overview of our presentation, first I'll just run through the hurricane itself. I'll show you the path and the strength of the storm before focusing in on its impact in Florida. Then I'll talk a bit about what we actually did in our survey and the approach taken during our investigation. So this includes using a new app to collect a high volume of data on a large number of houses. And then I'll start showing you the damage that we studied in 2 locations, and then I'll pass it off to Emilio, who will walk you through the rest of the observations and conclude by talking a bit about what we learned in this experience as young researchers. In the later half of the presentation, we're going to go through quite a few different photos of failure, but I think that these each show you kind of unique stories. And every community, even those that were in very close proximity to one another, had different sets of vulnerabilities that they had to face this storm. So hopefully we show you some interesting photos and give you some neat information. So to start, this map just shows an overview of Irma's path and a timeline. So the first alerts related to Hurricane Irma were issued at 11 a.m. Atlantic Standard Time on Wednesday, August 30th. At this time, the storm was located 420 miles west of the Cabo Verde Islands off the coast of Africa. So the first public advisory for Irma forecast the potential for hurricane formation within 48 hours, but actually only 24 hours later, the storm status was upgraded to hurricane. And due in part to the speed at which Irma grew, we expected it to become quite dangerous early on. So we were all kind of glued to our radars at this time. This map just shows a bit more precise wind speed history of Irma's landfall in the Caribbean and Florida. At its greatest strength, Hurricane Irma made its first landfall on the islands in the east of the Caribbean region, including Antigua and Barbuda. This started around September 5th, and it didn't weaken much as it continued across over the Dominican Republic, Haiti, Turks and Caicos, and finally Cuba. You can see that it kind of briefly downgraded to a Category 4 before strengthening again and hitting Cuba as a Category 5 storm. By September 10th, Irma made its first landfall in Florida at the Cudjoe Key as a Category 4 hurricane, where a 106-mile-per-hour gust was measured. After this impact, the hurricane quickly weakened, and its second landfall on the west coast of the Florida Peninsula occurred at Category 2 wind speeds. So this just gives an overview of Irma's impact. First, there are 75 total fatalities related to Irma across all affected countries. The rest of these numbers below here relate only to Florida. So the media reports state that as many as 6 million people were subjected to evacuation orders, but here we see that 116,000 of those evacuated to shelters. Power loss was also a widespread issue. And in addition to discussing the wind damage from the hurricane, we're going to discuss the damage related to tornadoes and storm surge in this talk. So related to the wind damage, which is one of the modes that we were studying here, this map shows the range of straight line wind speeds throughout the state. Excuse me. These contours are based on the Applied Research Associates model, fit to surface level measurements wherever those were available. And here, these points just show all of the tornadoes that were also confirmed by the National Weather Service on September 10th and September 11th. Later in the presentation, I'll talk about structural damage caused by one of these tornadoes, which occurred up in the corner at Crescent Beach, Florida. So in this work, the focus was on the performance of residential structures, especially with regards to wind damage. Our surveys in the northeastern part of the state were guided by Dr. David Roosh from Auburn University. And the longer venture in the southwest was led by Dr. David Pravat and Dr. Kurt Gurley of the University of Florida. We also traveled with a UAV pilot who took aerial footage of certain neighborhoods to help track the extensive damage and identify roof damage from the ground. In other regions, including Miami and the Keys, researchers from Florida International University, the Florida Institute of Technology, and James Cook University in Australia were also involved. The coverage of the entire study included an estimated 1,100 structures, and collectively all teams took over 5,000 photos of exterior building damage. So our talk is going to cover the surveys in the regions that Emilio and I personally attended, which are shown in this map. The portion of ground surveys that we participated in with the University of Florida covered much of the Florida Peninsula. The damage surveys in this region involved external ground surveys of neighborhoods with reported damage, or those which were reportedly hard hit. New damage survey methodology that has been implemented recently included use of the Fulcrum smartphone app, which I'll talk about a little bit just to give you guys an overview. So the Fulcrum app provides customizable forms for collecting geotag data. Its advertised uses included many construction applications such as infrastructure inventory and inspection reports. So the Applied Technology Council on their website provides a number of documents related to evaluating the condition of buildings following a hazardous event. The form ATC20 was the basis for the form that we used in the Fulcrum app. So during our surveys, we split into teams and canvassed different neighborhoods. At each residence, we would conduct an external survey. This would include taking overview photos of as many faces of the home as possible, as well as targeted images of significant damage modes. So on the next slide, I have a bit more detailed example. Each of the survey team members logged into different user accounts that were members of the Central Hurricane Irma Fulcrum group. As members of the Hurricane Irma group, we could just access the survey form and use it to store and sync data. So in an example here, you can see all of the points that I stored in this region on the left, along with details of the properties of the property at 505 East Coconut Avenue in the other figures. At each individual location, the form kind of looks the same. So near the top, you specify who conducted the survey. Then you can see the photos taken at that location, followed by building information, including address, then structural details, depending on what can be determined from the sidewalk. After defining the building, you fill in the cells related to the observed damage. So this form on the right here has a number of cells, and this is just a sample of the types of data we collected on each building. So we use the app tool and methodology mostly in the surveys in the Southwest, but before that we visited the Northeast near Jacksonville, where we got some practice using the app, but mostly focused on surveying the damage on pen and paper. So now we're going to start showing some examples of the types of damage observed in our surveys and take you on a bit of a tour through the communities we visited. So I'll start off by showing the residential damage we observed due to a tornado in the Northeast. We observed structural failure of the roof in this location, which was valuable for me to see since my master's research focused on similar failure modes that we saw. So as you can see in this first picture, the townhome units here experienced severe structural damage to the roof and upper floor walls. These units were situated right next to the beach running parallel to the coast. And then this overhead shot from the drone shows similar damage to the units further on shore. So those buildings on the previous slide were located just out the bottom of this frame, and behind them we saw additional similar damage in some units along an inland moving path. Looking more closely at the damaged buildings, we saw an interesting roof structure, which included these partial trusses over one span, then simple rafters or stick framing over the rest of the roof, which also included a large overhang as shown on the right. So this was interesting to me because, as I said, my master's research compared the performance of trussed and stick frame buildings under tornado wind loading. And it found that if hurricane straps are used, trusses should perform much better than stick frame structures due to nailed internal connections in the stick frame structures. Although in this case, the overhang and its framing probably played a role. Here are just a few more photos of the same structures and the damage we observed. So on the left here, I managed to find one piece of the stick frame section of the roof. And it landed upside down, but you can see the top plate of the wall, which would have ran the whole length along the top of the wall. And it actually failed through the wood section, and it came off with the roof rafters, which were fastened using hurricane straps. After Crescent Beach, we moved north towards St. Augustine and inspected some coastal homes that were severely damaged by what appeared to be a combination of storm surge and coastal winds. Just south of this location, the USGS measured storm surge heights up to 6 feet. And on the left here, you can see that the roof is gone, suggesting wind damage. But in other cases, such as the one on the right, it wasn't quite as easy to estimate where the progression of failure likely started. So here's just some more evidence of storm surge and its effect on building foundations. On the left, the foundation, which appeared to be screw piles, also appeared to be relatively intact, despite having the surrounding soil washed away. Alternatively, on the right is an example of a concrete pier, which was left completely exposed by rapid erosion. In this image, the piers here are actually, as I said, completely exposed. Excuse me. So they were hanging from the columns that they were actually built to support. So on the first day, we're focused primarily on that tornado damage. And Dr. David Roosh graciously guided us to view the surge damage at Volano Beach ourselves. So now I'm going to pass it off to Emilio to show you what we saw down in the south.
Hi, everybody. As Sarah said, I'm going to present some of the observations from our surveys down in the southwestern part of Florida. This started with Marco Island. We had a team of roughly 10 to 12 people, and we had split into groups, each trying to tackle a different neighborhood. As the picture indicates, we went into different directions and to try and cover more area. This screenshot from the app shows the damage me and Sarah collected, and the other teams created other points in Marco Island that they were also collecting. In total, over a course of 2 to 3 hours, we had covered about 215 buildings in the area. The majority of this building damage was minor. However, using the Fulcrum app, we're trying not to just examine the most heavily destroyed buildings. We're trying to just complete the data set. So we're looking at observations that are not as dramatic and just collecting data for minor damage to big damage, and the undamaged home damage is also important for determining the effects on the building code and help build statistics to better assess whether the new standards are effective or not. So here are some examples of the roof damage common in the area. As you can see, here are the estimated wind speeds of the day, which are considerably lower than the design wind speed set for the area, which have been increased since 2005. These were measured throughout Florida for Irma, and most of the wind speeds were below the design wind speeds. As you can see here, we just have some shingle damage and tile damage on these buildings. Next, we look here at a picture of Goodland. Goodland's located very closely to Marco Island, just south of it. We saw estimated wind speeds, again, of around 108, much lower than the design wind speeds. That had also been increased since 2005. On the image of the right, we see more of a failure to the greenhouse building there, while the building behind it has suffered little to no damage. There's no visible signs here. So one of the main causes of damage in Goodland was the storm surge. This is a very coastal area. There were neighborhoods here that were just docked right beside the shore with their boats just in the water there. As a result of the storm, there was significant surge damage. Here, the circled area indicates where we saw the line of surge damage. So pretty much everything underneath that point was all covered in water. In the following slides, we'll look at comparisons of homes that were subject to storm surge and the comparisons of what performed well and not so well. So here we have damage in Chokoloskee. In Chokoloskee, we see several examples of the newer elevated homes. These are trying to avoid the storm surge and flooding. A few mobile homes experience significant signs of this water damage. Overall, the Chokoloskee was considerably less affected, and there were many areas where there was very little damage due to the storm surge. In contrast, the nearby area, the state of Everglades City, which was further inland, experienced a lot more damage, which we'll be covering shortly. In both communities, the extent of the wind damage in this area is very limited to just minor roof covering and wall cladding damage. So here this map shows the relative locations of these two communities. Chokoloskee being a very island area towards the south, and Everglades City is more inland with the coast being further to the southwest. It was interesting to realize that Everglades City could be considered one of the hardest hit areas in the state, with significant residential losses due to the storm surge and flooding. Chokoloskee, a few miles away, performed very well for the storm. When our team was in Everglades City, there were several response efforts already in place, including large donation stations for clothes, bottled water, and tools. We were even there when the governor of the state was down. Much of the damage here, suggested by the photo on the right, includes internal damage and loss of belongings due to the water coming in and destroying everything in the homes. This was one of the instances where external surveys don't really provide an in-depth view of what is happening. From the outside, these homes may appear to be relatively undamaged. However, water damage inside of the home causes the structure to essentially be written off. This also causes gaps in the data for our purposes because sorry about that, because we're missing data in these sorry about that. There are gaps in the data of what we can and cannot track. The community suffered significant losses. Okay.
Emilio, are you able to share your screen again?
Yeah, just give me a moment. Is that good?
Okay.
We're back?
We're back, thank you.
Sorry about that, everyone. We have these little gaps in the data because of we can't tell the internal damages. This community suffered significantly due to the loss of utility access and the hazard and additional damage caused by the flooding in low-lying areas. A lot of the fatalities with these storms is associated with the floodwaters. In Everglades City, it was related to toxic floodwaters coming in. So here are more examples of low-lying homes in Everglades City. Although it doesn't look too much from the outside, you can see on the left here, there's considerable amounts of water in there. This causes internal damage to the building. And the building on the right here, you see it's a lot of mud and water on the outside. This is almost a week after the actual storm, and this water is still there. For this building on the right, while we were surveying, we saw teams coming in and starting to gut the building, as the result of the storm damage would cause these buildings needing significant amounts of repairs or demolition. So here we have more damage in Everglades City. Here's one of the homes that was actually pushed off of its concrete blocks. Before the storm, it'd be sitting on these concrete piers, and when the storm hit, it was knocked down. The outer edge of the deck was standing at the correct height, but you can see that the base of the home is now lying directly on the ground. And this would be a result of wind damage, and as this building's now off its foundation. So another thing we examined in the storm was the buildings that were made to be more resilient to this kind of damage. Our friends in Port Charlotte and Fort Myers wanted us to travel to look at the IBHS Fortified construction homes. The Fortified Building Homes program was a program set up by IBHS to essentially find people who were about to retrofit their homes, come down there and offer them some, it's like some sort of compensation so they could try new methods of designing homes that were better storm resilient. This was for hurricanes, tornadoes, and hail risks. And it upgraded things such as roof decking, roof covering, and underlaying wall systems of vertical load pathing, impact resistance, sheathing, corrosion resistant connections, and opening protection. This would be done for older homes where they were looking for an upgrade to kind of just see if we could improve existing infrastructure. Because Irma was not at a design level event, the performance of many of these elements was not tested to their fullest extent. We saw minor roof covering damage in fortified homes and neighboring homes. So in East Naples, the last community visited on our investigation, we observed the most severe straight line wind damage in the southwestern regions, which occurred to several structures in mobile home parks. We started in the west area and we moved along a stretch of single-family homes. Here we observed minor roof covering damage of the site-built structures. Just to the east of these neighborhoods, we found severe damage in the mobile home parks. After we surveyed the street to the west, we actually had the UAV pilot use a drone to seek out areas of more severe damage. This led to us to a nearby mobile park. So here we have some damage taken by our UAV pilot. He had several drones taken for this event, and here we see some of the most severe damage, with damage to the roof structure, multiple sheathing losses, and a lot of shingle loss in this case. We also saw damage to the built-on patio structures. These mobile homes had a significant portion of roof covering and sheathing damage, which is quite different from the nearby areas in comparison where we saw significantly less damage. So we inspected these mobile homes and the nearby remaining debris more closely. We saw that the mobile homes had original aging asphalt shingles and plywood sheathing, which had been retrofitted with panels of metal roofing. Shown in the foreground of the image on the right, and you can see the torn sheathing along the edge of the first roof. So here are some more images of mobile home damage in the neighborhood. As you can see on the left here, we have the outside structure, we have significant damage to the roof covering, and the one on the right, we have more damage to the roof covering, and some of the insulation of the building has come out, been blown out, and you see considerable amounts of debris. So this kind of concludes our tour of the southwestern peninsula of Florida. So to summarize our observations, most of the damage we found was generally minor, but it was widespread, covering almost all areas that we investigated across the state. The northeast area had more tornado, storm surge, and wind damage in the area, and towards the south, it was more storm surge and wind damage that was being the driving force behind the damage. The severe damage occurred in more isolated cases, such as examining tornado damage. It was a very isolated area, and then outside, it was considerably lower amounts of damage. All the maximum wind speeds that were recorded that day were below our current design wind speeds. The difference in these wind speeds for older homes could be some of the older homes designed for lower wind speeds could be a direct cause of why they were more damaged. The houses here were key to our investigation. We can't comment on the extent of the damage in the Keys, in the Keys, because we weren't able to go down there. But it was surveyed by others. Here's a picture from the Florida Keys, and it shows the evidence of what storm surge looks like from the inside. This home was likely going to have to be completely rebuilt or just demolished because of all the water damage on the interior. Although things remain in place, everything below the line of mud on the wall was completely underwater. So things that me and Sarah personally learned from this experience, we had not previously worked much with hurricanes. More of our work has been with tornadoes. So participating in this investigation, we learned it was a pretty big, interesting, and educational experience for us. To list some of the things that the two of us learned on this throughout from this damage survey were, for one, we quickly realized that hurricanes are very different from tornadoes in what you need to inspect. With a tornado, when you examine a severe tornado, it's just complete destruction and there's not much structure left standing. Here, in a hurricane, it's much more widespread. There's more things damaged to a lesser extent, degree of damage, however. There are a number of hazards here that can act together. In a hurricane, there's water damage and the wind damage, whereas tornadoes are more a singular wind event doing all the damage. From the ground surveys using the apps, we quickly became familiar with these apps and realized how much of a tool these could be for surveying in the future. The ideal goals with this app from the University of Florida are to start implementing it so that we don't necessarily need people just specifically trained for damage surveying to do all the work. It's more to do with crowdsourcing, where we can get more people to help with the damage survey, and then we can collect even more data in a quicker amount of time, rather than driving people everywhere with trying to get larger teams to cover the area. We also learned the importance to inspect all the houses, including which failures to put in the data set, and to overemphasize certain failures or because they could be neglected. We also noticed some of the difference between the Florida homes and the Canadian homes, such as the different tiling they're using. Most of the homes use clay tiling down there and stucco walls, which is considerably less common here in Canada. We also don't have fallen palm trees on homes here, typically. Personally, we also learned that damage surveys in disaster situations often require a lot of adaptability and flexible planning. We were very fortunate in this experience to have our UAV pilot, Quasi, with us, because it was able to give us additional benefits of being able to look for things in the sky and provide kind of a view that we wouldn't previously had. We also learned for any trip to always be as prepared as possible. We weren't sure what we were going into, really, and so we packed as lightly as possible, but as crucially as possible to make sure we got all the right things. So in closing, we'd like to thank our friends at the ICLR for helping us be able to go on this trip, that we are very grateful for being able to go on this opportunity. Additionally, we'd like to thank our friends down in the University of Florida. Dr. David Pravat and Dr. Gurley and Dr. Roosh were very helpful in helping us with the actual surveying and figuring out where the most damage would be to go from site to site. And we'd also like to thank some of the grad students we met, Jack, Rodrigo, Jason, Karthik, and Andreas, for pretty much being part of the team that we were able to survey with. And we'd also like to thank Quasi Perry for his work. He helped us a lot with the damage surveying and was able to provide aerial support. We'd also like to thank the financial support of Florida Building Commission and the National Science Foundation Rapid Award through Notre Dame University. So I'd like to thank you for listening, and I guess we'll open it up for questions.
Yeah.
Okay, thanks very much, Emilio and Sarah. Very interesting work and some good findings.
Yes.
So first, actually, I should say there have been a couple of questions about the presentation recording, and we should let the attendees know that we will plan to, or we will post the slides on our website and post a copy of the presentation on our YouTube channel, ICLR YouTube channel, which is all available via our website, iclr.org. So first question is about your observations of damage and the design wind speeds. So if you're able to go back to slides 21, 22, you showed some examples of damage to homes, and you're noting wind speed design figures. So were these buildings that were damaged during these 108 mile per hour gusts, were they designed based on these wind speed requirements? And if not, why did they fail?
Yeah, so these two homes in the Goodland area, the level of damage that we saw in these were two neighboring homes, and it seemed a little bit out of place. I'm not too sure when these two homes were built. We don't have numbers on that, so I'm not sure which design wind speed, but even previous wind speeds were in this region were around, as it says, 130 miles per hour. But from the photos, it looks like it was mostly wind damage here, whereas most of the other homes in the Goodland area were damaged due to storm surge. So it's not clear whether maybe a small tornado or just a large gust hit these two homes at the wrong angle, but they seem to be anomalies in that area.
So by and large, you found in this specific area that the newer homes stood up well. Like, I'm trying to understand this picture on the right here. This is so you've got that gray clad building.
Mm-hmm.
That is on the same foundation as another building that failed?
Yeah, so it was kind of awkward to get a picture of these two homes. This was one example of not going onto the property unless the homeowner was home. So I was actually across a small canal trying to take this photo to be descriptive as possible. The house in the background, the gray 3-story house, looked brand new. And even after the storm when we were there, it looked like it had just been freshly polished off and it was intact. We didn't notice any roof damage or anything. And the house just in the foreground in this photo, so just right next door, the top floor at least was totally demolished. Yeah,
okay. And so you're suspecting that it's possible that the buildings that were demolished, where you have, say, a home that stood up well versus a home that was demolished, like in this pretty severe comparison here, mm-hmm. the home that was fully demolished may have experienced wind speeds that exceeded the design figures.
Yeah, so it's hard to say. There aren't ground recordings in every region, and we didn't have any reports of tornadoes in this area. But it's also not clear how much older the greenhouse was from the gray house behind it. And the photo on the left was a house that would have been just kind of offshore from the greenhouse. So it could have even been damaged due to debris from the greenhouse kind of blowing over. Okay. But we didn't find the debris from the greenhouse anywhere.
Okay, oh, interesting. And I guess a related question is, being familiar with some of the work that was done in Ontario following, for example, the Angus tornado, mm-hmm. Where there was evidence of, code requirements not being met, and as a potential factor in the damage, was there any evidence of that sort of thing during your tour?
For the most part, I'm not sure as like how the Florida building code set up. A lot of the damage we saw was mostly in sequence of what we would expect. It was Angus, for example, had events occurring out of sequence with walls coming out before the roof had gone. Here, most of the events were in sequence, and most of the damage was relatively minor for the most part. The most severe damage was the tornado that we had saw in the northeast, and the damage there was all in sequence with the roofs coming off, then the walls coming off. So it doesn't lead me to believe that it would be construction or not up to build the code standards for failure.
Yeah, and if I could just add, this was in tornado damage, as we said, we kind of focus on the most severe damage and move in different directions to identify a path, length, and width. In a hurricane, there's such a large volume of damage and such a large area of land to cover that with this Fulcrum app survey, by the time it reached almost sundown, we were kind of surveying as many houses as we could in as short of time as possible. So we didn't look too closely at some of the details unless we saw surprising damage.
Okay. Thanks. So some other questions we've got a few questions from our online attendees here. One question was about roof attachments like solar panels. Did you observe any homes with solar panels? Any observations about damage to these types of homes?
I observed some of these like solar panel attachments when we were looking at the IBHS homes that had been retrofitted. In these areas, though, the solar panels were still on. However, there was not much damage in the nearby homes, so the whole area looked relatively unaffected in comparison to our more heavily hit areas. So it wasn't a good indication of whether or not these fixtures on roofs would survive a hurricane or not.
Okay. Another question about specific types of structures that might have been affected. Any insights about performance of screened enclosures, especially those designed to post 2004 Hurricane Charlie?
Right. So we saw in that mobile home park in Naples, we saw a number of kind of like porches and screened in enclosures and that way that looked like they had been built on after, obviously, if it was a mobile home. Many of those did not fare very well, even in the locations where everything else was unaffected. I think we kind of saw so many destroyed porches that we didn't really focus too much on those.
There was also, while looking at the retrofitted homes, in some of the more gated communities, they had screen enclosures for their pools and such. These areas were relatively fine with very little damage on the whole structure. They had nice roofs and such that were relatively undamaged. Most I saw was a little bit of debris damage due to clay tiles flying off. Okay.
Thanks. Question about wind speeds. I guess specifically referring to the slide that's up here. How far away were the stations that recorded these wind speeds, and do you have a sense about how reliable the wind speed data is in these cases?
Yeah, so I think this wind speed was taken from that contour map that we showed earlier in the presentation, which were based on models of the event, and a number of recording stations. I'm not too sure how many and how close they were, but they were just kind of correlated to those locations. Can't really comment on the accuracy or the kind of the height adjustment for these wind speeds.
Mm-hmm. Okay. To clarify, the estimated wind speeds are based on the ARA model estimates. Mm-hmm. That's true?
Yes.
Right. Okay. Another related question, is there merit in citing station data and then correlating that to damage at individual locations, excluding the local effects due to terrain or other damage sources such as flying debris?
I believe so. That's kind of an EF scale-esque assessment, right? Assessing damage and correlating it back to an estimated wind speed that would be assumed to cause that type of damage. Sure, if with the lack of on-ground wind speed estimates, I think it would be valuable to work back through the damage that we saw. Might be a bit of a task, but
yeah, having the contours and the estimate kind of gives a rough range, but having that EF scale, we look at damage and work back from there, as Sarah mentioned. So kind of using the two together might be the most beneficial way for damage surveying.
Yeah.
Again, we're trying, as I was saying with the Fulcrum map, we're just trying to collect as much data as possible. And if we can relate everything back to kind of figure out this final wind speed, that would be the ideal place we would like this to go.
Okay. So getting back to that, you had a slide there showing, I guess, some damage to a fortified home. And you were saying, so in the case you did go and track down a few of the fortified homes, and you compared the damages to neighboring homes, and so you found that there was no real significant difference in damages. Could you discuss that in a bit more detail?
Yeah, so we had, IBHS provided a list of homes that they had retrofitted, and we had gone to each of these sites, and we would try and take a look at the home that they had given us, and we would go around to check all the others in the nearby neighborhood that were also retrofitted. For the most part, we found that these homes were experiencing relatively the same amount of damage. There was one case, for example, where the fortified home lost a couple shingles. I would say between 10 to 20% of the shingles. However, when we went to the nearby homes, we were up to about 40 to 50% of shingles lost.
Okay.
This was pretty much the most damage we saw in any of the fortified homes. For the most part, we checked there at the place, and it would have very little damage, and nearby we might have threshold of damage on the nearby homes.
Right.
Kind of describe what you're interested there.
Yeah, right. So I was just interested in understanding a bit more of the detail there. So another question, you had a slide also showing, one of your first slides, Sarah, you were showing a home that had sort of a combination truss roof and stick-built roof.
Yeah.
So this home here, there would have been a wall extending all the way out to the far edge of the building, and the wall is missing. Is that correct?
Yeah, so this is kind of the end face of a long strip of townhomes. And you can see that the end wall is missing in addition to the coastal side edge of the roof.
Right.
So with the truss running just over halfway, spanning roughly half the length of the roof.
Okay.
This was interesting because, as I said, it's this truss structure with a partial stick frame segment. And the stick frame segment was the one with this roughly 6-foot overhang to shade the balcony below. And we found a lot of blown off balconies. There were some houses that didn't have quite this much damage, but it was just kind of like the whole balcony tore, or the whole overhang for the balcony tore off.
Okay. And so then to clarify that, the stick-built roofing framing was just over an overhang and not over an interior part of the building.
It was over the interior part of the building, spanning between the inward edge of this truss out to the edge of the room. So in the photo on the left, there was a room above this section where there's no wall or anything anymore, and then a balcony.
Okay. So can you draw any conclusions here or on the performance of that stick-built roof? It apparently completely failed, and the truss roof.
Yeah, in the next photo where we kind of show the wall top plate, that was interesting because they took the steps and added the hurricane ties to connect to fortify that roof to wall connection, which is what we like to see, but then the roof went anyways. And that's kind of what one of the conclusions of my master's work alluded to as well, is that the stick frame roof, unless you fortify every nailed connection, you still have nailed weak links in that vertical load path. But I also think in this case that overhang really didn't help.
Yeah, the fact that it was attached to an overhang.
Yeah, exactly.
So it really doesn't make sense that they would have fastened that to the building with the hurricane ties and not accounted for the load path throughout the rest of the roof framing.
Yeah, exactly.
And so that's what occurred. Do you have a sense of how the Florida residential code relates to this? Does it have specific provisions for all of those connections in the stick-built roof that maybe weren't followed?
Not that I know of. I know that the stick frame roofs are generally quite prescriptive designs. And these, I think on the previous slide, it says that these townhome units were built back in the 90s, with some of them being replaced more recently after another tornado that occurred. But as far as following or not following code goes, it looks like they followed code in terms of adding hurricane straps. You'd think they would have done their due diligence elsewhere. But I think that the stick frame design, at least in Canada, from my knowledge, doesn't involve any kind of ties at the other connections.
Yeah, great. Okay. So getting back to, I guess, the issue of Canada. So Canada is where you came from and where you had some of your previous experience. What are some of the general conclusions that you might draw from the work that you did down here that would apply to the Canadian context?
You want to take this one?
Sure. Well, for the most part, down there, we see some differences. We don't typically have surge damage here, so that's not as relevant. We're more interested in the wind-related things for our work specifically. In Canada, we use more of the shingle tiles where they use the clay tiles. We found there that the clay tiles were subject to damage easier than our shingle tiles. We also had they had significant amounts of soffits failures in like destroyed homes that we had seen, so that might impact us. I talked to one resident who he had soffit failures in his home, and that pretty much led to all the rainwater getting in. So that's something that we could very much see possible here in high wind events with large amounts of rain. The tornado.
By soffit, do you mean the cover of the soffit or the entire?
Yeah, the cover of the soffit.
Okay.
We also see the tornado damage seen in this image here. We have similar kind of events up here. It looks like it has improved in design. However, going back to the example seen here. The buildings that were destroyed were the older ones, whereas right beside them, they had the ones that were recently rebuilt, and those ones all survived the storm.
Yeah, they were, mind you, they were a little bit further off the path of the tornado, but yes, these were the older units in this whole complex. And if I could also add, in Canada, I guess we don't see coastal wind hazards as often, so some would argue that hurricane straps and fasteners and improvement methods like that might not be worth the homeowners or the contractors' money, but seeing that this was tornado damage, there is value in tying your roof down, even if they kind of missed the next weakest link in this particular house. Homeowners here in general, as we canvassed all the neighborhoods, we ran into quite a few friendly faces, and they were also thankful that their houses were designed to withstand this event. So I think there's definitely value in looking into fasteners like hurricane ties, even though they have the hurricane name in front of the device. I think there's value for things like that in Canada for sure.
Okay, thank you very much. So you focused on residential here in your presentation. Did you look at any other structure types, specifically engineered structures?
Yeah, so here we focused on residential structures because they do result in the highest losses, both for insurers and for the homeowners. You certainly don't want to see anybody end up homeless after an event. So we didn't really stop too much at other types of structures or institutional buildings or anything like that. But in passing, we saw kind of typical failures like the leaning or fallen over hydro poles. We saw some roof loss on a high-rise building that Quasi actually captured with the drone. So that was pretty cool. And then we saw things like gas station canopies torn off. A lot of water damage to strip malls in the Marco Island area. But other than that, there wasn't any major damage that we saw to engineered structures.
To add to that, most of the areas we walked through were residential. A week after the storm, they had got most of the big grocery store chains back up and running. In the plaza we stopped for in Marco Island, there was some roof damage, like small roof damage to some of the nearby buildings. A bigger issue for some of the owners there was the fact that some of their electricity wasn't going to work and such. We actually spent some time down there helping one shop owner move some of their stuff because the existing building had some damage to the interior roof, pretty much. So mold and such. So they wanted to switch locations, but the extent of the more commercial building damage was significantly less than what we observed in residential structures.
Okay, great. Thank you very much. Well, we're getting a little bit close to 11 a.m., so I might wrap it up here. But before we do, Emilio and Sarah, any last comments?
One thing, going back to this hurricane or this tornado damage on the wood framed house, one thing that occurred to me since coming home, I went to an event with the building industry regarding wood frame structures and wood frame construction. And I found it really interesting that there were no presentations that mentioned trusses anymore. Like trusses they're getting older now, but they were not too long ago kind of the hot new topic in residential construction. And that's what my research focused on. And we found a couple potential issues with truss construction. But the construction industry moves so fast to new products and new proprietary systems that we kind of skip over certain gaps that still need to be discovered as we introduce these new systems into the building code and into use. And it seems that code changes from our end that would improve the structural performance, such as hurricane ties, are usually quite slow going. And I found it interesting that new inventions and hot new systems get implemented so quickly without kind of second thought about the wind effects.
Yeah, it's interesting.
I guess
Sorry, go ahead, Emilio.
Takeaway was, it's interesting where we're going with damage surveying. It's like with Environment Canada, when I first started, it was pretty much show up at the location and write down a couple things and try and get out the reporting. It's like we've slowly implemented that system to be better with kind of a template and like a form to fill out. And with looking at how they're trying to do it in Florida, it's just slowly pushing to the point where we can try and finish things even quicker. With the Fulcrum app, it's a lot of, we're just going to try and cover as much as we can as quickly as possible because it's such a wide area to include. Also, on this trip, we got to see what additional tools can help us with, such as the UAV pilot having drones for us. That I find greatly benefited our scope and surveying. Like the images we were able to capture, one of the ones I remember most fondly is we saw a boat that had been completely blown out off the coast into pretty much a sandbar in the middle of a lake. So he just took his drone out there and he got a full view of what happened to this boat that
we really couldn't get a better view any other way of, unless we were going to find ourselves about.
Yeah.
So it's interesting that where damage surveying is going with the tools we might have, and pretty much how we can more streamline the process to get this kind of information out quicker and maybe easier to use for future people.
Yeah, I definitely see the value in that app for sure, even for tornado damage surveys. It was awesome that Dr. Vat and Dr. Gurley kind of let us work with this new technology and showed us around. They showed us a lot of hospitality. So I'd love to close with just thanking them once again for welcoming us down there.
Okay, great. Thanks again, Emilio and Sarah. Great presentation, and a reminder that we will be posting the slides and a recording of the presentation within the next few days that you'll be able to access via our website. Thanks everyone for joining and for the questions online, and we will be back with our Friday forums in mid-January, and we'll have Andrew Wiens from Associated Engineering in Canada talking about stormwater modeling under changing climate scenarios for urban subdivisions. So thanks again, Emilio and Sarah, and this concludes the webinar.
Thank you. Thank you very much.
Thank you for having us.